later. But the idea for this period is that if you have an oscillation, that oscillation can interact with what's called a medium to create waves. So let's put this all together. The oscillation in this case is this up and down motion of this spray can. The guy starts the spray can. That oscillation has an amplitude, a period, and a frequency. But when it interacts with the medium, that's the material that it's traveling through, when it interacts, it then creates a wave. That oscillation interacts with the medium so that its motion spreads out over a large area. How oscillations make waves is they start with their own period, frequency, and amplitude and interact with the medium near it. Waves are going to be periodic motions, so they're going to have amplitude, frequency, and period, but they're also going to have two new properties: wavelength and wave speed. Wavelength is going to be how wide is your wave, whereas amplitude is like how tall is your wave. Wavelength is going to be how wide is your wave. And wave speed is going to be how fast does it travel across the room or across the lake or across the depths of space. So let's say I have a sound wave. My sound wave starts with an oscillation. It starts with this oscillating speaker that moves back and forth through magnetism, like we worked on in our test. And it interacts with a medium. The air around the speaker is going to start to vibrate with the same frequency. So I'm going to draw on my wave here. I start with an oscillation. It interacts with the air, and then it travels across the room. So, with propagation of sound, with how sound travels, a common misconception is people are like, oh, well, it's just the air from the speaker travels into your ears. It's actually not. Each individual piece of air will vibrate with the same frequency, and that vibration spreads across the room until it gets to you. Especially if you're in the room, it is not air from my lungs going into your ears. It's air from me shakes this air and this air and this air and this air, and it shakes all the way until it reaches your ears. So the only air that's going into your ear is the one that's right next to it already. So oscillations are the source of all waves. So if I can start with some sort of thing in oscillating motion, and it pushes on the air or the water or the earth around it, then you can create a wave. This is kind of a funny picture. This is a violin string in super slow motion. So in this case, I have a transverse wave on a string. As this wave travels, it pushes on the air around it. But you see how the string doesn't touch a lot of air on its own? That's why there's that big resonating chamber on the back of a violin. All the air inside this hole is going to shake at the same frequency that that string is. So the string vibrates, that shakes the chamber shakes the air, and then it travels shaking all the way across the room to you. So that oscillations are always the source of waves. Kind of a funny one that we'll talk about more when we get into the light unit. Sometimes with light, people are like, well, where does the shaking come from? Where's the oscillation in light? The oscillation in light is a little trickier. The oscillation in light is that an electron in a high energy state loses energy. It falls down to a low energy state and emits that difference in, I guess, the difference in energy, emits it as a wave. And I drew mine kind of out of sync, but I'm trying to make the blue wave match up with the blue wave. With light, the source of vibrations that starts a light is an electron that moves to a lower energy state. Inside the atom, the electron moves from high energy to low energy, but energy is conserved. So if it loses electric potential energy, it's going to emit light so that energy is conserved. Don't worry about for this test where light comes from, because we'll do a whole unit on light in the future. So now let's talk about the two new properties. We know that all oscillations have amplitude, period, and frequency, but waves also have wavelength and wave speed. So what is a wavelength is how big is the wave laterally. So take two corresponding points on adjacent waves. So let's say take from crest to crest on wave blue. I'm going to draw this in yellow. Crest to crest on the blue wave is 470 nanometers. Normally, if we're doing it on life-size objects, we would do centimeters or meters, but since light is really super duper small, we would do nanometers for its wavelength. So I could measure this from crest to crest or trough to trough. And as long as I pick two adjacent points on adjacent waves, it doesn't matter which I pick. So notice that all three of these yellow lines are the same length. Now the symbol for wavelength is a lambda. If you have trouble drawing this for yourself, you can draw it like this. Draw it as kind of like an upside down Y. Wavelength, lambda, is measured in meters, and it's telling you how wide is your wave. So frequency tells you how many cycles it does per second. Wavelength tells you how wide is it. Let's add on one more thing. Because before we go to lab, I want us to understand resonance, nodes, and antinodes. So next, watch this video from Physics Girl about standing waves.